Hey developers, I'm Tom, and I'm excited to share with you a journey that drastically transformed my game engine's performance. If you've worked in game development like me, you know that achieving smooth and responsive gameplay is a constant pursuit. Today, I'm going to take you through how focusing on reducing heap allocations more than halved frame time. Many game engines are written in C++ because of performance. However, this game engine is written in C# using sharpdx to interact with DirectX. It could be faster if it was written in C++, but this is a project of passion. Now let's dive into the technical side of things. To work out how to reduce memory allocations, first we must understand the stack and the heap. Stack is where we store small, short-lived data. Every time a method is called, a new frame is pushed onto the stack, which stores the method return address, as well as the local variables. It's fast and efficient because the allocation is as simple as changing the value of the stack pointer. Consider the two methods shown, renderSquare and renderLine. How could the execution of these simple methods be modeled on the stack? As we see in the animation, every time a method is called, we can push a stack frame containing method parameters, locals, and the return address onto the stack. The return address is needed so we know where to resume execution after the method is completed. This is apparent in this example with renderLine method being called 4 times. When returning to renderSquare method, it needs to know which call completed and resume in the correct place. On the other hand, we have the heap, which is where we store larger, long-lived data objects and arrays. The heap is more complex as it has to keep track of where objects are allocated and has to keep track of which space is free for new objects. C# is a garbage collecting language, meaning it will periodically clean up data from the heap that is no longer referenced. It is fast, but still is causing micro-stuttering in the game. To track down allocations, I've been using the .NET Object Allocation Tracking tool built into Visual Studio. Other tools exist like .cover and .memory by JetBrains, but this tool is more than suitable for what I'm going to show you. The goal is to use the tool to reduce frame-by-frame heap allocations of the engine in debug and release builds to 0. At this point, goal has failed, but it has been significantly improved. Additionally, by reducing heap allocations, we should also improve frame rates. This goal has been a success and at least halved frame times. As we can see from the diagnostics reports I've kept from the tool, it has taken at least 29 iterations to get to this point. The reduction in file sizes over time are a good indicator for the reduction in heap allocations. Here is the first report from the tool. We can see that it peaked at a huge 100,000 objects during startup. We can get a visualization of the micro-stuttering as a sawtooth wave in the live object graph. As we can see from the first 1 second interval of the game running, there is over 1 megabyte of float 4x4 allocations. This brings us to the first easy change. Make float 4x4 a struct. At this point, I should note in the video, I will demonstrate code that violates the Microsoft design guidelines on choosing between class and struct. Microsoft constantly violates these guidelines themselves as well, so I don't feel too contrarian. See the link in the video description for the guidelines. Structs are value types, meaning that they are declared on the stack except when they are boxed or on the property of a class. This is great as it means we can eliminate all but a few heap allocations of float 4x4. There is an important difference to consider when making a class a struct. Structs are copied by value. This shouldn't be a problem for small types, but it can be costly with larger types. Float 4x4 is not small, but not too large either. Where appropriate, we can use the rest keywords to pass a stack reference into the method to avoid copying by value. Eric Lippert has a fantastic blog article on Microsoft Learn titled "The Stack is an Implementation Detail." You can find a link to it in the video description. As well as changing float 4x4, other types that are primitive to the engine were changed as well, shown on the slide. Another easy change was to use for loops instead of for each loops. This report shows that there is an enumerator being allocated because of boxing. However, it only seems to allocate if the collection is an interface. For example, iList. I do not know if this is still the case in a release build, but I've changed them to for loops so that they don't pollute the diagnostics. Now this brings us on to the change that had the biggest impact on the performance for the engine. The engine uses constant buffers on the GPU to store constants to the rendering of a given frame, for example, the camera's transformation. I've put arrows next to all the allocations this change eliminates in the diagnostics report. A rough calculation using just the data in the report shows approximately 22 megabytes being allocated on the heap per 1 second sample. Comparing the new and old code, it should become clear where the problems come from. Going through the update method, the first thing it did was call a getBytes method, which allocates a new byte array the same size as the buffer and use Marshall structure to pointer to copy the data into the array. Once we have the buffer data represented as a byte array, we then call map_subresource to get a stream to write data to the GPU, writing the entire byte array to the stream. In the new code, instead of copying the structure to a byte array and allocating a temporary data stream, we instead use a different overload of map_subresource, which returns a pointer to the subresource buffer. sharpdx provides a utilities.write method, which uses interrupt.write under the hood to copy the data structure directly into the subresource buffer without any unnecessary allocations. The result was a drastic improvement in the frame rate. As mentioned earlier, various primitive types of the engine were changed into structs to avoid heap allocations, including particle. Particle is a large type due to having various properties you need to track over time, for example, position, rotation, color. Particles define an update method that needs to be called by the particle pool. Now it is a struct, we need a way to update it in place, avoiding copy by value semantics. Using the collection Marshall, we can get a span for the particle pool collection. Luckily, span defines an array accessor that can be used to get a reference to individual items in the collection without copying. The final piece of the puzzle was to make the particle update method static and take a reference to the particle as an argument. Now particles can be updated in the pool without allocations and avoid large portions of data being copied. Another common source of heap allocations is boxing of value types. An easy way to unintentionally box is calling object.equals on the value types. Because it takes an object as an argument, it must first box, then use reflection to compare the types, making it even more inefficient. See the link in the video description for a link to the framework design guidelines with more information on the matter. These two blocks of code show two implementations of a very similar property on two different classes. The bottom implementation has no constraints on t-value and would be inefficient when calling object.equals. The top implementation has a constraint on t-value, ensuring it implements iEquatable. This means that it does not need to box the argument, as we know it must be a t-value, the same type. There were various other changes I made to reduce the number of heap allocations, many very similar to the ones shown. Doing a before and after, paying close attention to the number of live objects and private bytes, we see a drastic reduction from about 100,000 live objects peak to 31,000, and a reduction of 37 megabytes in allocations. Okay, next slide. Additionally, you can see now that the live objects graph more slowly grows and is thus not garbage collecting as often. Ideally, this would not grow at all, but that would require a lot more work in the future. Thank you for watching. If you had a similar experience in the past or just have some advice or something I've missed, please just leave it in the comments below.